Okay, so we have an exam coming up on the 27th. So that's in 3 class days. So I want to do quiz 2 on Tuesday so I can get it back to you next Thursday. So you'll be able to see questions that might potentially be on the exam before the exam. So next time we see each other, quiz 2, chapter 2, it will only cover the stuff up to what we cover today. So that's going to get into the pollution stuff, but it's not going to go through the entire chapter. So I will send out an email or a Canvas message saying what sections you're responsible for. And so you'll be aware of that for the quiz. And then the exam should cover all of chapter 1 and chapter 2. And so your guided notes will be due the day before the exam. And I'll look at the videos for chapter 2. They will probably be due right around the same time. So if you haven't had a chance to look at those, do that as well. So any questions about things coming up? All right. So we are going to go back to doing things on your guided notes, but I am going to make a little bit of a detour. So we will get to question 10 is basically what we're going to work on in the last part of class today. But we're going to talk a little bit about charts and graphs. So hopefully for most of you, you recall this from your K-12 experience. But just in case you weren't paying attention that day in class, we're going to go over a couple of things. And then on Tuesday, we're going to look at specifically some of the charts and graphs that are in your book and interpreting those. So while this isn't specifically material that is in chapter 2, pretty much every quiz or test from here on out, I will have some kind of a graph or a table or something for you to interpret. So that's why we're going to go through this material. All right, so up. Turn this on. So hopefully this will start making noise in a minute. There are lots of different types of graphs. All of them are going to have some features that you should be looking for if you ever need to make a graph. I know some of you are taking the lab with Dr. Hamilton. If you need to make a graph in lab, there are some things that you should pay attention to when you are making a graph as well. So first, some general tips. In general, your graph needs to include labels. Usually you'll have a title in the book. This might be part of the caption. It might just, like, the first line of the caption basically be the title. This is what the graph is about. Then, except for pie charts, which are not on axes, you should have the axes labeled. So for a bar graph, a line graph, a scatter graph, those are types of graphs that you can make if you use Excel. The vertical axis and the horizontal axis, you need to tell what you're measuring, and you also need to know how you're measuring it. So, if you're measuring pollution, what is the units? Are you doing parts per million? Are you doing percent? Are you doing, molarity is another way you might measure something. So you would put what units you're using and what it is that you're measuring. We also want to make sure that anytime we have a scale on the X and Y axis, that we make sure that the scale is very even. So we don't have, a 5 halfway through the line and then all the way at the end of the line, it's 200, because that makes the first 5 parts look just as big as the last 195. So you want to make sure you have even representation as you're going through on your lines. So if you have a bar graph or a pie graph, you're going to have categories of some kind. And so you need to make sure that you label those individually. So like on a line graph, I'm measuring how much something is changing. But for a bar graph, I might have the categories of what year it is, or I might have the category of what class I'm taking, or what college or university this represents. So I need to label each one of those so that people know what those bars or wedges on a pie graph looks like. And then anytime you have numbers, you should put units with that. Now, of course, on a pie graph, those numbers are just going to be percents, so we're not going to worry about that so much on the pie graph. But for everything else, we need to make sure that we have units. So units are things like grams, parts per million. Those are the things that tell us what those numbers represent. All right, does anybody still need this slide?
Is this from number 8?
This is not in your guided notes.
Okay.
Okay, so one kind of graph that you might have is a pie graph. And this is a pie graph that I just pulled off of the internet. And part of it isn't done very well. So I'll talk about that in just a second. A pie graph should represent the percent of something. So what you're showing is that the whole pie is 100% of everything. And then each wedge of the pie is what percent that category represents. So I shouldn't have a pie graph where I'm only showing 75% of things, because then it doesn't add up to the whole, okay? If I'm making the pie graph, the way I figure out how big the wedge would be is I would say, okay, what is the percent? Let's say I had 55%. I would put 55 on the top and divide that by 100, because remember, a percent is per 100, and multiply that by 360. What is 360? Where does that come from? That's the degrees in a circle, right? You remember way back when you learned about circles, there are 360 degrees in a circle. So if I have 55% of 360, then I know what percent of the degrees that I would have. So I would have just over half of those percents. And so this wedge here that is 21%, we would have 21 divided by 100 times 360, and that would be equal to this angle that is in here. That's how you would come up with that. Now, if you're not writing a graph, you wouldn't have to know how to do that calculation. But if you in lab get asked to make a pie graph, that's how you would do it. Now, if you have something that is less than about 1 to 5%, the wedges are not really big enough for you to see anything. And this is where this graph breaks down. So this is showing 0.93 for argon. That's how it's labeled. That wedge is a lot more than 1%. And then we have a wedge for carbon dioxide that's almost the same size as the argon, but it's only about 1/20th the amount. So again, it's not actually showing us very well the representative size. So for carbon dioxide and other gases, we basically wouldn't be able to see the wedge that was in there. So that wasn't done very well on this graph that I grabbed off of the internet. It would be better if you're trying to illustrate to people how small the amount of carbon dioxide actually is in the atmosphere, to show that it's just a tiny little line that you can't see, whereas this makes it look like it's much more than it actually is. Okay, bar graphs. Sometimes these are called column graphs. So each of these represents different categories. So you can see I have these labeled as the gases in the air: nitrogen, oxygen, argon, and carbon dioxide. So you can see from this graph, where I'm measuring the percent, you can really see nitrogen is a lot more than oxygen. That's easy to see. Now we could see that on the pie graph, but what you can also see here is the argon is barely visible. So those of you in front might be able to tell there's a little green piece here, and you basically can't see the carbon dioxide and the other gases because they're too small to be seen on this type of a chart. Okay. So bar graphs are going to represent data in categories. We need to be measuring the same thing about those categories. So in this case, it's the percent, but I don't want to be measuring, let's say, grams of one chemical, and then for another chemical, instead of grams, I'm measuring concentration. I'm measuring parts per million. I want to measure the same thing for each one. So usually it should not matter what order you put the categories in. It doesn't change the information if I decided to do this in alphabetical order and do argon and put that over here and then put N and O after carbon dioxide. That wouldn't have really changed anything other than just the way the graph looks, but I'd still be able to get the same information. Where people get confused sometimes is if our bars represent years. So if I say this is the total number of people who graduated from Georgetown each year, because a year is a time frame, then people get confused and think, oh, I need to have a line graph. But in that case, you can't really graduate, you know, midway through the semester or 1 week into the year. So really you need that whole year to contain the number of people who are graduating. And when we have something like a year, yes, we do put them in numerical order. Does it matter? Could you still get the same information if I mixed up the years? You could, it just would be confusing for the people reading it. So the one exception to that rule of the order is usually if we have years or months, you would, sorry, I bumped this. I think it's coming back. You would be able to have the, I think it's coming back. No, oh, don't do this to me. There. Okay. Yeah, so you get what I was saying. Anybody lost on what I just said? Okay, because I don't want to like add to it and make it more confusing than it needs to be. Okay, don't forget to put a scale on the vertical axis here. So sometimes people have this bar graph where you can tell the differences, and nitrogen's a lot more than oxygen, but if you don't have a scale, you don't know how much it is. So we might look at this and say, oh, that's almost 100%, but it's not really 100% because our scale only goes up to 80%. So make sure you have a scale on there. All right, so something that you will see sometimes is a stacked bar graph or chart. So this allows you to put more data into the bar graph sometimes. So I might have one category that I divide up information. So maybe I want to have, these are each of the years that people graduated from Georgetown, but then I wanted to divide up how many of those people were science or math majors, how many were humanities majors, and how many were other. So I could see the total amount of graduates, but I can also see the portion that changes each year. So I could see, oops, I could see that, you know, that red portion got really big in the second year and then small again in the third year. Okay, so this allows us to put more information in. So each thing, which is labeled as a series there, so that each part of the bar, each subcategory there should be measured in the same units. So I shouldn't be measuring my humanities majors in individuals and my science and math majors in percents. I want to make sure I do it in the same units. So this allows us to compare things as the whole category or as the subcategories, which are called series here. All right, I forgot to check what's on this link, so I don't quite remember, but I think this is an example of something from 2022 that has these kind of graphs. So this will be exciting. Wonder what it is. So this has to do with the pollution. One kind of pollution is called particulate matter. So PM is particulate matter. And then the 2.5 tells us how big it is. So 2.5 is really small particulate matter. And if we click on, let's look for something in Kentucky. This looks like Lexington. Okay, so let me find Lexington on here. Yeah, there we go. Okay, so we're looking at Lexington on both of those. Okay, so we can see the total amount of pollution, but then we can see the categories of pollution. And so if you have a graph like this, you're going to want to look for the key for what the different sections of the bar look like. So what seems to be the biggest part of the pollution, particularly around 2002 and 2004? Which bar is the biggest? If you can't read it, what color? Yellow? Yeah, so yellow is here. This says sulfates, and we'll talk about that as a kind of pollutant. And then you'll notice there's just a tiny little black bar in between the red and the green. Okay, and that is elemental carbon. So elemental carbon is found in what resource that is mined in Kentucky? Coal. Yeah, so we're probably going to have more elemental carbon than you would find in many other states, just because the mining industry is going to put some of that into the atmosphere. And then one thing that doesn't appear to be on there at all is that blue category, which is sea salt. And that makes sense because we're nowhere near an ocean. Okay. And you can see that the red box got a little bit smaller over time, but basically is pretty much the same. The green boxes stay pretty much the same, but the yellows over time are getting smaller and smaller. So we could maybe interpret this to say overall pollution is going down, and in large part that is due to sulfate pollution going down. So this allows us to draw two conclusions from the same graph. Okay. All right, let's go back to our PowerPoint. Yep. Okay. Sometimes you will see a graph like this, a color gradient map. You're probably most familiar with this with weather. So basically the idea is we use different kinds of colors to show us the intensity of something. And then the map is showing us the location. So rather than having an X and a Y, what we do is we say, well, here's the location. And then we're using the color to give us how big it is. So the color represents the amount. And we need to make sure that there is a key. So we should be looking for the key. And I took this one out of your book and it did not provide a key. So this is an air quality index where green means we have really good air. Yellow means it's a little bit problematic. And orange or red means that it's unhealthy. Red being more unhealthy than the orange. So that's something that you would need to be looking for. If we saw this graph with some kind of a article about it and it didn't have a key on the graph, that might make me skeptical as to, is this really what this graph is representing, or did somebody just choose this graph and decide to write about it? Are they lying to us? Or maybe they're not interpreting it correctly. I like to be able to go back and look at the graph and make sure I can see it. So that's something that you can look for if you're looking at a website or an article about something. Make sure that graph is giving you the information you need to interpret it. All right, other features of the map may provide additional information, such as location boundaries. So we have the boundaries between states here. So we could say, oh, is this red spot in Kentucky? And hopefully you know your geography well enough that even if this line weren't there, you would know that no, it's not in Kentucky. But we can tell, because the line is there, that it's both in Texas and in Oklahoma. So we have both of those to give us information about that. Okay, and then sometimes if there's something that is significant, like the red spot, maybe we want to know what big city is near there so that we can have more of a context. So that might be highlighted on there as well. The other thing that's given on this map is some geographical features. So what geographical features are shown on here? What natural landish features are being shown? So one obvious thing is that we can tell the difference between the water and the land, right? We can tell where the Great Lakes are. We can tell where the oceans are. If we look closely in eastern Kentucky, eastern Tennessee, eastern Ohio, western Virginia, North Carolina, what is that region? I think I heard somebody say what? Appalachia. So there are darker areas here representing the mountains. And then over on this side, there's also darker green areas representing the Rocky Mountains. So we have both of those. Okay. We also might have tables that give us information. And this one definitely is hard to read with the light on. So let me turn this off. So this is the color scheme that the map before was referring to. So the green, I told you, was good. Yellow, they call that moderate. And then once you get into the orange, this is where it starts being unhealthy. So orange is unhealthy for specific groups. So that might be people who have asthma. Air quality would be bad for them. Or elderly people are more susceptible. And so if you go to the air quality index webpage, they detail who are the people that are most at risk. But once you get into that red category, then it's bad for everybody. So I pulled these numbers this morning off of different weather locations. So Lexington and Louisville are the cities near us. So what category do those fit into for air quality? Good. Okay. So we look at the number, we can see on the left-hand side where that range is, and then we can see what it is. So if we were to look at the weather page for that, there might be just a colored bar, or there might be a line between green and then yellow, orange, and red, indicating where we are, but we're in the good category. Indianapolis and Panama City, Florida are just edging out of good into what category? Moderate. So you might think about Indianapolis, it's a little bit bigger than Lexington is, but so is Louisville. So, you know, maybe it's not just that it's bigger. Maybe Indianapolis just isn't as good as cleaning their air. So that may be problematic. There are also geographical features that make a difference. So Indiana is very flat. Some cities like Nashville kind of sits in a valley, and so it's hard for air to move out. Its air quality tends to be a little bit lower than that because of that. I looked at Cleveland. It's raining in Cleveland, and so their air quality index is more in the good category just because the rain is washing out the air. Florida sits right on the ocean. Actually, Panama City is on the Gulf Coast, but it's got the air currents, the ocean air. Usually Florida has pretty good air quality, but you'll see later why that and Houston are a little bit higher right now. And then I was kind of surprised about this. New York City, I looked there because I thought, oh, surely New York City will have really bad air quality, but they're actually one of the better ones on here. So, all right, so that's interpreting charts and graphs. Now we are going to switch over and specifically look at different kinds of pollution. And so this is where looking back at your guided notes will be helpful. So these are the pollutants that are in that table. They're also the ones that are discussed in sections 2.8 and 2.9 in your book. So the first thing that we want to know is, what do you need to know about these pollutants? So your questions on your quiz may ask you for the name or the formula. So when I say sulfur dioxide, you should be able to give me the formula for sulfur dioxide. If I give you CO, you should be able to give me the name carbon monoxide. And that's where some of that naming of compounds that we did on Tuesday is going to come in. So we should be able to go back and forth between the names and the formulas. For each of them, I'm going to give you some characteristics. So things we're going to be interested in, is it something we can tell by looking at it? So some pollutants are colorless and we won't be able to see it. Some are orange, so we would be able to see it. Some of them have a smell and others don't. And so you wouldn't be able to tell by the smell. It's odorless. So those are some of the things that we would be looking for. And then we want to know what's the source or the cause of the pollution. So there are certain ones that, depending on where you live in the country or what's going on around you, might be more predominant. And then, of course, if it's a pollutant, you want to know how that affects you. And so we're going to look at the impacts on your health. Secondary pollutants are going to be pollutants that can result from the first pollutant. So sometimes we'll have a pollutant and then it reacts with something else in the air and makes another pollutant. So we're going to see that ozone can be made a couple of different ways. And one of the ways it can be made is as a secondary pollutant to the nitrogen oxides. Okay, so those are the things that you're going to want to be looking for and be ready to talk about. Now, we won't, I don't think, get to secondary pollutants today, so you don't have to worry about that for the quiz, but we will get to it next week, so it will be on the test. Okay, so we're going to start with carbon monoxide. This is one that's really important to be aware of. You may have a carbon monoxide detector in your house. A lot of times people put this in the wrong place. They'll put it in their garage or they will put it by their front door. And carbon monoxide is something that happens when we have insufficient burning. We don't have enough air to burn something. So this might happen where you have your furnace in a basement. It might happen in an enclosed workshop or man cave, or it might be in a place if somebody has a heater that they use because it gets cold in this part of the house. My daughter's bedroom is the coldest part of the house always. So that might be a place that we might be concerned about whether or not there was carbon monoxide. So it's best not to put those detectors where there's lots of breezes. It's more in closed off areas, particularly if you're heating something there. It is called the silent killer, not because it doesn't make noise, but because it is odorless and colorless. You can't see it, you can't smell it. So you're not going to know it's there unless you have that carbon monoxide detector. All right, we good here? Okay, so what does it do? So first we have to talk about what oxygen does. When we inhale oxygen into our lungs, we have red blood cells. So this truck represents a red blood cell. The wheels actually kind of look like red blood cells. They're disc-like and they're sort of dented in the middle. And those red blood cells have something called hemoglobin. You've probably heard of hemoglobin before. And the oxygen attaches to that hemoglobin, but it does it in a reversible way. Just like putting a battery into something and you can pull the battery out and put a new battery in and you can go back and forth. So oxygen does that. The red blood cells move the oxygen from your lungs to every place else in your body where you have cells, and then it offloads the oxygen so that it can do the things it needs to do. And then the little truck, the red blood cell, goes back to the lungs, picks up more oxygen, and the process continues. So oxygen is just two oxygen atoms bounded together. Carbon monoxide is two atoms bonded together. They have the same shape, they're right about the same size, but they lock in just a little bit differently. So the carbon monoxide can fit into the same location, but it's like that battery that's like stuck at the very bottom that like you can't really get your fingers around it, you can't pull it out, you turn the thing upside down, you're trying to bang on it, you can't pull it out when it's dead. Okay, and you're trying to pull the screwdriver or the tweezers to get it out, and it just won't come out. That's carbon monoxide. Okay, so the problem isn't that carbon monoxide is doing something, it's that it's keeping the oxygen from getting there. So all these red blood cell trucks are full of the carbon monoxide, they head out to the body, and your fingers and your toes are like, I need oxygen. And they're like, oh, sorry, we don't have oxygen. We have carbon monoxide, but it doesn't want to get off. They go back to the lungs. The carbon monoxide still doesn't want to get off. And you just over and over again, you have this carbon monoxide traveling around your body and no place to get that oxygen in. So really it's about suffocation, about depriving your body of oxygen. So the problems, the health problems we see are related to the fact that we're not getting enough oxygen. When you don't have enough oxygen, you might be dizzy. Like if you hold your breath too long, you might be dizzy. You might feel weak. You might feel sleepy. You might have a headache. Sometimes people get nauseous. That's usually after long periods of not having the carbon monoxide. You might get confused. And you might lose consciousness. And this is one of the problems with it. You know, say you have your little space here, you're in the basement where it's cool, and that's where you're doing your Lego tower that you like to build, and the carbon monoxide builds up, and then you get sleepy. Well, you lay down on the couch or whatever, and you're still in the same place where you're not getting oxygen. So that's where it can become really dangerous, is you're not getting to a place where you have the oxygen. The best cure for this is to get outside and get into a place where there's a lot of oxygen. And then eventually you'll get enough of that oxygen to replace the carbon monoxide. It'll statistically just be enough of the oxygen to push it out. Okay. So if you have a carbon monoxide detector go off in your house, the thing to do would be, you know, open the windows, go outside. That's what you would do. Okay, questions on this page? No. All right. This is one of the main reasons why, like the small little grills that you can buy, they say don't use them indoors because there's not enough air to really burn that fuel completely. It's not so much that it's a fire hazard, it's that you're creating carbon monoxide. Okay, next one, sulfur dioxide. This is one of the chemicals that I have on your videos, a longer thing, but it's an episode of a TV show. So if you like The Crown, there was an episode of the TV show that had to do with sulfur dioxide, and you can watch that for 2 of your video credits. Okay, so this one, easy to detect, sharp, unpleasant odor. You're not going to want to be around it. It's going to hurt your eyes. It's going to hurt your nose. It's going to hurt your lungs. Okay. This, along with the nitrogen oxides, we'll see the same thing for it. When they hit water, like the water in your eyes, the nose has mucous membranes, your lungs have water in them. All of that creates an acid. So sulfur dioxide plus water is creating, this is called sulfurous acid. Okay. So the problem isn't the sulfur dioxide itself, it's that it turns into an acid, and the acid is burning. So we said, does it create a secondary pollutant? Yes, the sulfurous acid is a secondary pollutant. So where this comes from is burning coal. So coal, how did it get into the ground? Where did that come from? Old dead things, right? So dead dinosaurs, dead plants, long, long ago, died off. Our bodies, aside from the water, are mostly carbon, and that carbon over time gets compressed down, and after however many centuries, then you get coal. But our bodies also contain sulfur in them. So the DNA that makes up our body, the proteins that make up our body have small amounts of sulfur in it. So all the coal that comes from dead plants and dead animals and things like that has sulfur in it. And so when we burn those things, that can end up in the atmosphere. Now, some sources of coal have a lot of sulfur, some have less. Nice thing about Kentucky is that we're sitting on this coal field that is very low in sulfur. We have some really good quality coal here. Other parts of the world, that's not so much the case. So these are 2 locations that had significant events where a combination of burning a lot of coal. Now, we don't have in our homes coal burning stoves as much as was the case when these things happened in the mid 1900s. But there was a lot of coal burning either in the homes, or there was a zinc factory in Pennsylvania that was burning. Then we also had weather where the air was not moving, so we're not blowing the air out and getting fresh air in, and something called a thermal inversion. So we know hot air likes to rise. In a thermal inversion, that air gets trapped and it stays in place. So for 3 or 4 days, the same air with all this smoke getting into it was pumped into the air. And in England, this happened in December when it was really, really cold. So people weren't going to be like, well, I'll just stop burning coal. And they would have frozen. So they kept burning the coal. So we're producing a lot of those sulfur dioxides. That gets into the lungs and that hurts people. Okay, so we talked about this a little bit, burning in the eyes, burning in the lungs. This is what it might do to a plant. So we see these orange, yellow spots on there. So it kills off the plant. Acute respiratory distress. Respiratory refers to what part of your body? Lungs, yeah. So this acute distress might be, I can't breathe, okay? And like all respiratory things, it's particularly bad for very young, the babies, and for very old people, grandma. It's bad for people with asthma, bad for people with emphysema. So emphysema is a respiratory disease that's more common in elderly people and people who've been around either cigarette smoke or other kinds of smoke, depending on their working and living conditions. COPD, you may have heard of that. That's another lung-related issue. So people who have those systems are more susceptible. So if you have people in your family that you know fit into those categories, when the air quality index is very high, that's when you need to be talking to those people about, oh, let's make sure we get you to a place that has good air. This also leads to acid rain. So like we said, it forms that acid. So we can get acid rain. And it damages foliage. So foliage is a word for leaves, plants, okay? So this is showing damaged foliage. And it also decreases plant growth. So maybe the plant doesn't have spots on it, but instead of growing as much as it would, it stays small and doesn't produce as much as it would normally. All right, are we good with sulfur dioxide? All right, nitrous oxides. Very similar in their result, source is different. So we say NOx because there are like 5 different versions of nitrogen and oxygen that you can make. There's NO2, N2O, N2O5, N2O3, N2O4. So rather than saying each of those individually, we just say NOx. It's a combination of a lot. Some of them are colorless, so nitrogen monoxide is colorless, but nitrogen dioxide is kind of a brownish orange color. Okay, so this is one that you could see. And if you are in a city that is in a valley, sometimes you'll see kind of an orange haze. I think this is a picture of Los Angeles. A lot of times that orange haze would develop when you would have a buildup of the nitrogen oxides. So where does it come from? Well, remember our atmosphere is a lot of nitrogen. So if you heat the air, you are going to produce some of these. Now, it's not because you're burning the fossil fuels per se, because the fossil fuels mostly have carbon in them. But when you're burning it, you're making the air around it hot. So that it's the hot air that is turning into these nitrogen oxides. So this can happen near power plants. This can happen around cars. So if you have Los Angeles, a lot of people drive rather than taking public transportation. So builds up a lot of this stuff. But the other way it can happen is with forest fires. And we really saw examples of that last summer and fall during their fire season. So for me, I normally think of like, okay, California, yeah, they always got fires going on. I'm always hearing about something. Feel bad for them, but that's over there. But my daughter last summer was doing an internship in New York, and there were fires in Canada. And so it got to the point where they were having trouble breathing and whatnot, where she was working in northern New York, not the city. She was at the northern part of the state near Canada because of that crossover. And in fact, so much of it crossed over, it did get down to New York City. And so I don't think I have a picture of on it, but I remember seeing a time-lapse video of the weather changing from kind of cloudy to orange to you just can't see anything over New York City over the course of one of those days. Okay, so it's not just the dust and the smoke that's in the air, it's this nitrogen oxide that's in the air. Okay, and much like the sulfur dioxide, it combines with water, it's going to form this acid. So this is nitric acid, and this is a really bad one because it acts as an acid, but it's also what's called an oxidizer. Oxidizers make chemical reactions occur more readily. All right, anybody still need this slide? All right. So it is very reactive. These are, if you've ever heard of free radicals, many of the nitrogen oxides are free radicals. And free radicals are like wild Tasmanian devils that just go crazy and react with everything around them. Okay, so they produce a lot of other pollution too. So one that we'll talk about later on is VOCs. That is volatile, which means it turns into a gas, organic, carbon. And so anything that has carbon, like our fuels, our gasoline, can form these volatile organic compounds. And when we have these nitrogen oxides that might be formed near a hot car engine, they're going to react with those and form ozone, which is another pollutant. Okay, so all of these pollutants are getting together, making things worse than they would be individually. And as for the effects, much like I said before, much of the same things that we would see with sulfur oxides, and it does produce acid rain, so we're going to decrease our plant growth. We can see this forest area, instead of having, these are all pine trees, you would expect pine trees to be very lush and green year round, and they basically have no leaves on them. Acid rain will also damage limestone, and particularly in areas like this where limestone is abundant. For over a century, it was very common to make buildings, statues, and gravestones out of limestone. And so if you go through the Georgetown Cemetery, it's really hard to read some of the older limestone graves because the rain, which is a little bit acidic, has washed away the features of them. So you can imagine in areas where that acid rain is worse, there's just nothing you can read. All right, we good with this, or we need this slide more? Okay. Ozone. So we'll talk about ozone a lot in the next chapter. So ozone is a molecule that has 3 oxygens. So this is an allotrope. Remember the word allotrope? When we have an element, only oxygen there, but it can have different forms. So regular oxygen, 2 atoms. Ozone has 3 atoms. Okay, so this is an allotrope of carbon. And this one is very reactive. It has a distinctive odor. Some people find it unpleasant, but some people don't. It smells electric. So a lot of times if you're near a copier and it has a distinctive smell, because the copier runs off of static electricity, you can kind of smell the ozone there. If there are high concentrations, it can be very sharp. It is formed naturally in the upper atmosphere. What layer of the atmosphere? Do you remember where we would see the ozone layer? Stratosphere. So that's what one of the things I'll probably ask on your quiz. You want to have that little chart with the layers of the atmosphere so you know where the ozone is. Okay. If it's in the troposphere, that's where all the living things are, including us. And then it becomes a pollutant. So when it's in the stratosphere, it's not touching anything living. We don't care. It's doing good up there. Down here, it's a problem. And it comes from nitrogen oxides and VOCs, and also from sunlight. So sunlight can cause that reaction to happen. And as I said, it comes from like there being electricity. So if you think about the biggest zap of electricity of all might be lightning. Lightning can form ozone as well. When it's problematic around here, it's usually more because of the pollution of nitrogen oxides in cars and things like that. But lightning does produce ozone. So this sunlight portion is something to pay attention to. This is a really short-lived compound. It reacts pretty quickly. So it's not going to stick around for days and days and days. And so since sunlight is what produces it, if you have really sunny days, you're going to make more of it. If you have rainy days, ozone's going to be less of a problem. So over the summer, if you pay attention to the ozone report, usually the ozone is higher, the air quality is worse for ozone when we have those stretches of like 2 weeks with no rain. All right, so what does ozone do? So on people, like all our respiratory things, it reduces our lung function, okay? It can cause you chest pain. It's going to irritate your lungs in such a way that your immune system would respond. And your immune system responds to irritation by making mucus. So it's going to cause congestion, coughing, and spit and stuff. And like all of the other air pollutants, it's especially bad for people with asthma and emphysema. Especially bad for the really old and the really young. In the environment, it's going to damage leaves. So it's going to mottle them. So you can see here we have like the lighter spots and the darker spots, a little bit of orange too. So it's a little bit different from the sulfur dioxide. I'm not going to pick on what those differences are. It damages leaves. That's what we want to know. It also inhibits plants doing photosynthesis. That's how they make oxygen, but the ozone keeps the plants from making oxygen. So that's a bad thing because we want more oxygen. And then just like it would harm our lungs, it's going to harm the lungs of any animals that are out there. Your pets, your dogs, your cats, the deer in the environment. Another thing that it can do, because it's very reactive, is that it can react with plastics that we have. So plastic and rubber, tires, if you have containers that you keep things outside that, you try to keep them dry, they might become brittle over time because of exposure to ozone. All right, questions on this page? Okay. Lead. Nope. This one. Yeah. All right. So lead. Lead is something that with your generation, you've probably heard about it more and worry about it more in water supplies. You are probably still old enough that you remember hearing about Flint, Michigan and their water issues. Do you guys remember that? Okay. I'm kind of getting to where that's been quite a ways out, but yeah, they had issues with lead in their water supply, but lead in the air is also a problem. This was more of a problem decades ago when lead was used in lots of different places. So we're going to talk about what the source of lead is so we can understand why that is. So it is mined from an ore. An ore is like a rock that might have like one mineral that's really highly concentrated in what we want. So highly concentrated in an ore. And then you take it to the processing plant and they're going to add carbon to purify it and they're going to burn things and whatnot. And so it gets spewed into the air during this process of trying to purify it. A lot of older materials would have paint that had lead in it. So lead compounds were really good at having really bright colors. And so in the early part of the 1900s, anything and everything might have be painted with something that had lead in it. Particularly yellow was a nice bright color you could get out of lead. Pipes would be made out of plumbing, older pipes. That would more end up in the water than in the air. And then most car batteries have lead in them. So they're called lead acid batteries. The acid is actually the sulfur dioxide, or not sulfur dioxide, sulfuric acid that we talked about being bad for your eyes. but those batteries have lead in them too. So if they're manufacturing that or if they're disposing of that, then those processes can spew it into the air. When it gets into the air, it can travel pretty far. So if your lead processing plant is in Louisville, that doesn't mean you're necessarily safe out in Moorhead because it can travel pretty good distances there. So in addition to it being found in paints, for a long time, it was also found in gasoline. So when you put gasoline in early cars, it was discovered that sometimes just the burning process would cause a knocking sound. And that knocking would make the car less efficient. It wouldn't go as fast for the same amount of fuel. You would speed up, but then you go through all of your gasoline. But if you put certain lead compounds in it, that would make it run better and you could get more mileage for your car. And so it was seen for a long time as being, yeah, this is a great way to, get our cars to work better. But in the 60s and in the 70s, we started seeing some of the problems that you'll see on the next slide. And so mid 70s, lead was forbidden in paints and they started phasing out lead in gasoline. So this is why when you go to the gas station, it says it's unleaded gas. It's not like there was lead in your gasoline to begin with and they took it out. There was never lead in your gasoline, but they used to put lead in. So when I was a child, you could either buy leaded or unleaded gasoline. And now the only option is unleaded. Okay, so what does it do? This stuff is bad. Oh, this is another source one, sorry. So this one kind of shows you the difference that makes. And I wish these pie charts were colored because you can't really get a sense of what this is. But in the 1970s, the lead emissions, the things that were causing lead emissions, this big wedge here, 78% is on road. Okay, so basically more than 3/4 of the lead in the atmosphere was coming from cars in the 1970s. And if we look at the 1997, that stuff from, they don't have on road as a category on here, but they do have fuel combustion. So that includes cars, but also other kinds of fuel combustion is down to 13%. So we made a huge difference just by that policy change of saying, let's not put lead in our gasoline anymore. Okay, so what does it do? All of these things on this chart, I know that you can't see them, so I will read them to you. So we've got things pointing to our brain. Basically, lead can cause brain damage. The younger a person is, the more likely it is to cause the brain damage. So this can cause problems in learning, so learning disabilities, but it also can cause problems in executive function. So executive function is basically adulting, like your ability to sit still, your ability to not punch the person next to you, even though they keep tapping their pin in an annoying way. Your self-control would be affected, especially the younger you are, if there was lead in the atmosphere. It can cause problems in speech development. So being able to pronounce words properly, to be able to say words without stuttering, things like that. It can cause hearing problems. It can cause an increase in blood pressure. So this pointing to the heart says high blood pressure. This says anemia. Anemia means low iron in the blood. And so iron is what's in that hemoglobin that's holding on to the oxygen that's taking it to the rest of your body. So anemia would cause the rest of your body to be deprived of oxygen, which is what's causing some of these things. If your brain isn't getting the oxygen it needs, you're going to have brain damage. Causes kidney damage, digestive problems, reproductive problems. So adults would have difficulty conceiving or carrying a conceived child to the end of the pregnancy. And then reduce. Now, most important for lead compared to all the other things we talked about, all the other things, you have a problem with that, get somewhere with clean air, you're good. Your eyes are going to clear up. You're going to be able to breathe. You're going to be fine. Lead, whatever damage is done, is done. If you've damaged the brain of a kid who's grown up in an area where there's lead in the air, that kid is brain damaged for life. okay? Once you have those reproductive problems, there's no turning back from that. And that's why lead is such a serious issue. So if and when you decide to have kids, one of the first things that they do early on in life is do a blood test for lead. And that's to make sure that you're not living in an environment where your kid might be exposed to that. Older homes might have paint that had lead in it. Now, enough change has happened over time that you probably won't ever live in one of those homes. But the home I grew up in was built in the 1960s. So probably if I had been one of those kids that just put everything in my mouth, I would have been consuming lead. And kids do that. That's just kids. But there are lots of ways that an environment might expose somebody to lead, and that's what they look for. Okay, so questions about lead. All right. Particulate matter, PM. So this is divided into two categories based on the size. So particulate matter just means that it's either a solid or it might be like a little droplet of liquid with stuff in it. That would be microscopic. So basically either you wouldn't see it or it would just look like smoke to you. So we're not talking about big pieces of ash. We're talking about stuff that you can't really see. Okay. And the composition just kind of depends on where it comes from. So it might be from smoke. So then you might have little bits of like the carbon from the wood or paper or whatever that was in there. But if it is particulate matter that is coming from a factory, that might also have the sulfur dioxides or the nitrogen oxides in there. One thing that affects me, pollen. I am allergic to pretty much every living thing. So like February is like my favorite time of year usually. And this year it's not working out for me because it's so warm. But usually like when it's frozen solid, that's when I can breathe. And then the rest of the year, I'm just reacting to everything. So dust and pollen might fit into this category as well. The size matters. Now, this is something where bigger is actually a little bit better for you because the bigger particles are going to get caught before they get to your lungs. So y'all have nose hairs, and we don't like to think about our nose hairs, but our nose hairs have little bits of water droplets on them, or maybe little bits of mucus that are coming from our mucous membrane. And as we breathe in, the larger particles get attached to those. And then you maybe have to sneeze and out of your body, or maybe you get a little congested because remember, that's an immune response building up that mucus, and then you blow it out. But the teeny tiny ones make it past there and into your lungs. And once they're in your lungs, the tubes in your lungs are so narrow and fragile that these tiny little pieces can scrape against the walls and break up the cells and damage those cells. So that's why size matters. All right, so let's look at sizes. This is being measured in, I want to say nanometers. So this is almost 1 billion nanometers would be a tennis ball. A period on a piece of paper would be about 1 million nanometers, okay? So 10,000 nanometers would be a cancer cell. So 10,000 nanometers is PM, particulate matter 10. That's about the size that we can start to filter it out a little bit. Some of it's going to get into our lungs, but it's not going to make it all the way down to the teeny tiniest little tubes. But once we hit the 2.5 level, those are the particles that get into the teeniest, narrowest passages of our lungs, and that's ones that can do real damage. And then you can see other things like a virus is just a little bit smaller than that, maybe about the 10th the size of that. An antibody is something that is in your body to fight viruses or fight bacteria. And we have cells and different things, and then glucose is a sugar molecule. So those are even smaller still. All right, so big picture here, the smaller the particle, the worse it is. That's the main thing I want you to remember. And we call these particles PM for particulate matter. All right, so wildfires are going to have a lot of these things in them, but I mention it here because, of course, they're producing smoke. So we're going to have particulate fires. You also are going to get those nitrogen oxides because remember, you've got really hot air, hotter than your car engine, hotter than a power plant because it's such a large amount of fire in one location. So you produce this huge amount of heat and you get this orange haze. And so these are a couple of wildfires. We just passed the 6-month anniversary of the wildfires in Hawaii. Super devastating there. And I mentioned the Canadian wildfires. I think this might be that picture I was telling you about. Oops, go back. No, I can't get it. All right, this one should work though. Okay, so this is a map of current wildfires. Now they always have this disclaimer that pops up because they're like, please don't use this as to whether or not you should stay in an area because maybe we didn't see your wildfire. So that's why, yes, I understand that. But if we look at the map, we can see different places that have wildfires. So I mentioned earlier, Houston had an air quality index of about 95, so double that of the moderate level. And then Panama City, which is on the Gulf Coast of Florida, having a little bit of a higher index. So if you look in those areas, those are areas where there are currently wildfires right now. And that's why the air quality is lower in those areas. All right. We are getting just about to the end here. Last thing that I want to mention here is how we measure how dangerous something is. And we'll look at this chart more on Tuesday when we do our interpreting charts and graphs activities. But this is a chart that tries to put together all the information that we have about what you're allowed to be exposed to. So there is a risk of being exposed, which means it's potentially there. Doesn't mean it is there, that it's just, that's an environment where that kind of thing could happen. Okay. Toxicity is how dangerous it is if you are exposed to it. Okay. How toxic something is depends on the person. So we've already talked about how toxicity is going to be worse for people who are old, for people who are babies, for people who have asthma. Okay. So the big things that matter is how old you are, what your size is, how much you weigh. Your gender can matter because sometimes hormones influence things. And then your other health conditions. So like, do you have asthma? Those are things that really matter. Okay, that's toxicity. Now I'm going to ask you on your quiz and your test to distinguish between toxicity and exposure. So toxicity depends on you. Exposure depends on the situation. So this means how long were you there? How concentrated was it there? And how quickly you were breathing. Okay, so your exposure is just how much of it went in and out of your lungs. All right. It does not matter whether you are, you know, a 50-year-old man or a 10-year-old kid. It matters how long were they standing there, what was the concentration in the air, and how quickly they were breathing. Okay, so the darker blue column on this chart lists the concentration in ppm. What does ppm stand for? Parts per million. So what is the limit that we're allowed to have in the atmosphere at any given time before, you know, the government starts saying, I'm going to put a fine on this factory or whatever? Okay, so we have a limit for things like carbon monoxide, nitrogen dioxide, and ozone. Particulate matter, there isn't really a limit there. And I think that is probably because you have things like wildfires that can influence that are outside of people's control. So that blue column is saying what is the limit that we are allowed to be exposed to. If I want to have the limit be very, very tiny, does that mean that that is something that is really bad for me? Or that's something that's, well, it's not great, but I'll be okay. It's a teeny tiny limit. Really bad for you, right? Because the really bad things, you want to have the smallest limit to. So if I look here, my limit on carbon monoxide is up at 35. I don't want to be around carbon monoxide, but if I am, I just go outside and I'm okay. But this ozone, that limit is 0.07. That's something I really don't want to be around, okay? Sulfur dioxide down in the same range. Now, lead is something they never want in the atmosphere, so they don't have a concentration listed here. But they do have kind of a limit in other units. This is a different set of units of this is the limit that you should be exposed to before it's going to start causing damage. And so you can see this one, 0.15, is way lower than all the others. You do not need to know those numbers. You do need to know smaller is worse for you. So what I would do is give you the chart and then ask you, which is worse for you, ozone or nitrogen dioxide? Okay. I think that's the last slide. Yes. All right, so I will see you all on Tuesday for a quiz over chapter 2. Bring your notes. You will be allowed to use your notes.